Hi, I'm Professor Melko, Chemistry PhD, and today we have a lecture on Boyle's Law, Charles' Law, and Lusak's Law, which help us quantify exactly how the pressure of a gas is affected by things like temperature and volume. So let's just jump into the lecture. Here's Robert Boyle, who you'll remember perhaps from previous videos and lectures that he proposed the scientific method. Right? He actually used that scientific method to propose laws, one of them having to do with gas pressure. So in the previous video, you can go back and watch when we discussed what is gas pressure and how do we measure gas pressure, and what are the different units and factors that affect gas pressure. Robert Boyle actually quantified the relationship between pressure and volume. We mentioned last time that as you decrease the volume of a container and shrink it down, there's more molecular collisions with the walls, so more force exerted and thus more pressure. Since pressure is really just force over an area. So as you shrink down the volume of something, you create more collisions with the walls, so the force is going up per unit time, and so the pressure goes up. Okay? We discussed last time how this means that pressure and volume are inversely related. As volume goes up, out to the right, pressure goes down. As volume goes down, here to the left, pressure goes up. And so there's this inverse relationship here between these two factors. Boyle actually quantified this, and we have Boyle's law, P1 V1 equals P2 V2. Just note here that the unit of pressure in P1 is the same as the unit in pressure in P2. They could both be torr, they could both be millimeters mercury, they could both be atmosphere. Just make sure they have the same unit. Much like volume here, they can both be milliliters or both be liters. Just make sure they are the same unit. So here's how we're going to use Boyle's law. A lot of problems in gas chemistry will provide you with 3 out of these 4 variables, right? So you might be given a starting volume, and you change the pressure of the gas. Then you're asked to identify the new volume of the gas. Likewise, you could be given 2 volumes and asked to find the pressure. Right? So the problem here would be written something like this. Imagine a gas has a pressure of 3 atmospheres and the volume is decreased from 5 liters to 2 liters. What is the final pressure? Okay, so in that example, I gave you 2 volumes, 1 pressure, and asked you to find a final pressure. Right? So you would use a version of the equation like this. But these formulae here are just rearrangements of Boyle's law. Okay, so Boyle, remember, is always P and V. P1 V1 equals P2 V2. Let's see this in action. Here, feel free to pause the video and try to solve this yourself first before I go through and solve it. A sample of methane has a volume of 3.5 liters and exerts a pressure of 1,550 millimeters mercury. If the volume is then changed to 7 liters, what is the new pressure? Assume temperature and number of molecules of the gas is not changing. Okay, so as we go through this lecture, there's going to be a lot of problems like this, and you have to identify, is it Boyle's law, Charles' law, Lusak's law, or some other law? The best thing to do is read the problem through once, and then read it through again and identify each of the quantities given. So let's read this again. A sample of methane has a volume of 3.5 liters. V1 equals 3.5 liters. And exerts a pressure of 1,550 millimeters mercury. So I know that is P1. That is the pressure given with this volume. P1, 1,550 millimeters mercury. Good. If the volume is changed to 7 liters, this is a new volume, V2. What is the new pressure? So now I've identified each of the things given and what I want. I'm not worrying about temperature or number of molecules. I must need a formula that relates volume to pressure. That is Boyle's, right? Boyle's law says P1 V1 equals P2 V2. So now we take this formula and just plug in the numbers. P1 is 1,550 millimeters mercury. Multiply that by V1, 3.5 liters. This is going to equal P2. That's what I'm trying to solve for. Times V2, 7.00 liters. So I can see here I have this one unknown, P2. I want to get this by itself, so I want to divide both sides by 7 liters. So that it drops out on the right and appears on the left. And now I have my way to calculate P2. I take 1550 times 3.5 divided by 7, and I get 775 as P2. The unit here is going to be the same unit of pressure I was given. Why? Because the liters units drop out. Okay, so you might have an instance where the units are not the same. Maybe one volume is liter, one is milliliters. Make sure they're the same unit. Here they're both liters so that they both drop out. Okay, so here the final answer here is 775 millimeters of mercury. If the question asked for it in a different unit, you might have to do a simple pressure conversion. Go back and watch my previous video if you don't know how to do the pressure conversion. So that's Boyle's law. Charles came next, who figured out exactly how volume and temperature are related. We talked about last video that volume and temperature, okay, actually we talked about last time that pressure and volume and pressure and temperature are directly related, right? Which means also volume and temperature are directly related, okay? As the temperature of a gas goes up, that gas tends to want to expand or increase its volume. Why? Because it has more energy pushing on the walls and trying to expand the volume. So as temperature goes up out to the right, volume goes up on this axis. Okay, so temperature and volume here are directly proportional. Charles identified the exact relationship you would use in calculating temperature to volume relationships and named it after himself, of course, Charles' law. Here, though, the temperature must be in Kelvin, right? So back with Boyle's law, we didn't care what the units were as long as they were the same. When it comes to temperature, there's only one unit we want to use in this chapter or in this lecture, and that is Kelvin. Okay, so make sure the temperature here is in Kelvin. The volumes can both be milliliters, right? Or they could both be liters, or they could both be cubic centimeters, doesn't matter. But the temperature definitely has to be Kelvin for this formula to hold. V1 over T1 equals V2 over T2. So there's going to be similar type of problems with Boyle's, only here they're giving you maybe two temperatures in one volume and asking you to identify the new volume. Or they're giving you two volumes and one temperature and asking you to identify the final temperature. So questions like this might be written, 5 liters of gas at 300 Kelvin are heated to 600 Kelvin. What is the new volume? Right, so I gave you an initial volume and a temperature that was changing and asked you to identify the new volume. Then you would use Charles' law. So let's see this in a practice problem. Again, feel free to pause the video here if you want to try it yourself first. As always with these problems, I'll read it through first once. A 132-liter helium balloon is heated from 20 Celsius to 40 Celsius. What is the final volume of the balloon? Again, we're going to identify each of these parameters. The first volume given, I'll call volume 1, 132 liters, is heated from 20 Celsius. So T1 is 20 Celsius. That's where it's starting, where the volume is 132 liters. It's heated to another temperature, 40 degrees Celsius. What is the final volume? V2. Okay, so V2 is what I want to use here. I clearly can see that this is a Charles' law volume-temperature relationship. V1 over T1 equals V2 over T2. Remember here, while both volumes are going to be the same unit like liters, doesn't matter what that unit is, but that they're the same, temperature has to be in Kelvin, so I must convert this to Kelvin. Here I'm going to do the conversion by adding 273. Celsius going to Kelvin, we add 273. Sometimes you'll see 273.15. I'm not going to worry about those digits for this exercise. So adding 273 to each of these temperatures converts them to Kelvin. And now I have 293 Kelvin and 313 Kelvin. And now I can substitute these in my formula. Here's V1. This 132, I'm going to put in here. Here's 293. I'm going to put that in here. And here's T2. I'm going to put that in here. All right, so 132 liters over 293 Kelvin equals V2, what I'm trying to solve for, over 313 Kelvin. Now to solve this algebraically for V2, I multiply both sides by 313 Kelvin, drop it out over here, I multiply it on both sides. The Kelvin is going to cancel. And I'll be left with the unit of liters. So 313 times 132 divided by 293. And I get a volume 2 of 141 liters. Again, the unit that I have for the final volume is going to be the same unit as the initial volume. The last law we're going to talk about here is Lusak's law. So already Boyle connected pressure and volume. Charles connected volume and temperature. Lusak connected pressure and temperature. Okay? And his law looks a lot like Charles, so don't get it confused. Lusak had to do with pressure, Charles with volume. Lusak found that as you raise the temperature of a gas, the pressure raises. Again, as you're adding energy to these gas molecules, they're hitting the wall more frequently and harder, so they're creating more of a force and more of a pressure, right? Since pressure, again, is just force over area. So as the force goes up, the pressure goes up. As the temperature goes up, these molecules are moving faster and creating more of a force. Okay, so pressure and temperature are directly proportional. And it's quantified here with Lusak's law. Again, temperature here must be in Kelvin. Problems that ask you about Lusak's law will be written something like this. A gas at an initial pressure of 1.5 atmospheres is heated from 30 degrees Celsius to 50 degrees Celsius. What is the final pressure? Right, so there I gave you an initial pressure, a temperature change, and asked you for a final pressure. Okay, it's just recognizing that the pressure-temperature relationship is Lusak's law, plugging in the numbers given, using the same strategies we've talked about thus far, and solving for that unknown pressure. Or you could be given both pressures and one temperature. For instance, a gas at 300 Kelvin and 1.5 atmospheres has its pressure lowered to 0.65 atmospheres. What is the new temperature? Right, so there I gave you two pressures and one temperature, and you rearrange this Lusak's law to do something like this to find the final temperature. I'm not going to do a practice problem here because they're very similar to the Charles law practice problem and Boyle's law practice problem that we've done. Okay. Now, here's a summary of Boyle, Charles, and Lusak. A lot of times you have to memorize these, and you can do that by doing a bunch of practice problems, which you should do, but it can also help to remember this mnemonic. Okay. And I make this pyramid to remember this mnemonic. And at the top of the pyramid is B for Boyle. The lower right is C for Charles. And the lower left is L for Lusak. Okay? And I put P here, B here, and T here. At this vertice, multiply. At this vertice, divide. At this vertice, divide. And I have this mnemonic. Beyonce visited class today, learned plenty. And Beyonce is at the top of the pyramid because obviously Beyonce is at the top of the pyramid. Beyonce visited class today, learned plenty. Okay. Boyle, B, is P times V. Charles, what is it next to? V is over T. And Lusak over here is next to P over T. Okay. So Boyle is reading across P times V, Charles is V over T, and Lusak is P over T. So that's what's said here. Boyle is P times V, Charles is V over T, and Lusak is P over T. So that's a little mnemonic that I teach for how to memorize these three different laws. That'll do it for today's lecture where we quantified how pressure, volume, and temperature are all related. Next lecture, we'll get into the ideal gas law. As always, if you like this video, please press the like button and feel free to subscribe to this channel on YouTube. And check me out over on Twitch where I can help you every week doing office hours and answering whatever chemistry questions you might have. That'll do it for today. See you next time.